we are talking about shaders programming in lighting. So, kind of, if I see the coloring of the any primitive, I mean pixel wise, then I don't need to provide the color at the every pixel. We just need vertex position of the primitive name and colors and the model. It is a kind of a smooth model or flat model. That's it. And then it estimates the color. So if there are too many kind of vertices, then color will be smooth. If vertices are less primitives are there, then it will be coarse. But whatsoever. So the kind of the rasterization happens once we specify the color model and the color at the pixels. This is typical coloring in the kind of fixed function pipeline. Okay? In fixed function pipelining, if I don't want color through color, GL color, then still I want coloring. There is another way called lighting. There is another way called texturing. There is another way called texturing plus lighting. There is another way called blending. Whatsoever. Now, we are talking about getting the color of a primitive through lighting. Okay? Not providing GL color or whatsoever at the bottom. How it happens? Number one. Number two, in shaders problem. Number two, how transformation happens. I have a vertices. I have a kind of a model staying, and I am rotating, translating, transforming the light source. Or light source is stationary, and I am transforming the model. So one case is that how fragmentation for a lighting happens. I don't want GL color. And second thing is transformation what model wise or light color. So these two things that we'll see. So idea is that if I have a light source, and so like in pipelining mode, fixed function pipelining mode, we need to specify the light source and their various properties like ambience and its kind of emission, its diffuse characteristics, and its kind of shining property. So these kind of properties I have to set for the model, I have to set for the lighting. So if I set, then OpenGL does all the calculations. But in the shaders programming, programmer has to do all the calculations. There is no light source, nothing. So what programmer is expected is that, like in shaders programming, there are two things. One is vertex estimation, and another is rasterization. Okay. So we say that at each vertex, what is its position at the end of all the transport? Each vertex, what is color? What is color? Color model is it smooth or flat? If I provide this information, then Taiwan shader would do the kind of whatever you want. So there is no OpenGL. In shaders programming, everything has to be done at the GPU. Means all the vertices transformation calculation, all the color calculation. If it happens to GPU, GPU is kind of it's dumb. So we have to write everything in the shader program. So how we can if I have a light source and if I have a vertices, then how we kind of calculate the lighting at the vertices, and then how it will go into fragmentation. That is the first thing that we'll see. Second thing is that transformation, that how transformation happens. Like if I need to transform the model, but I don't want lighting transformation. If I want to make a model stationary, I want lighting, means light source is moving. So these calculations are kind of complex in shaders program. It's not that straightforward. Like if I use the fixed function pipelining, everything is available. Push matrix, pop matrix, and you just rotate the light source, and then in the model transformation push matrix, and when you do GL plus, everything is done. But problem with the kind of fixed function pipelining is very slow. If I have a kind of earth or aeroplane moving and these kind of, that it won't work. Means if vertices are in thousands, then we need to use GPU. If I need to use GPU, then GPU, the way it works is pretty much different. Means I have to it doesn't know what is lighting and what is the texturing or whatsoever. So like okay, so in texturing, at least in fragment shader, we do something. But in lighting, it doesn't know anything, light source or whatsoever. So how, like the way we specify the coloring at the vertices, how we will specify coloring at the vertices when we do the light calculation. So there are two models in the light calculation. One model is called kind of Goard model, that is per vertex calculation, and one is form model, that is per kind of per fragment calculation. Like if I have number of vertices are less, then a form model makes sense. When like if we do per vertex per fragment calculation, then it will be smooth. Whereas a kind of Goard model is very nice if number of vertices are too many. Okay, so right now we will kind of focus on Goard model where we do the lighting calculation in the vertex shader. So if I do the lighting calculation in the vertex shader, means per vertex we are specifying the color that we calculate through lighting calculation, not through external kind of just GL color or whatsoever. So if I have a kind of a light color, if I have a material color, if I have a light position, if I have a viewer position, and if I have a kind of vertices location, if I have normal, how I can do mathematics in a way that the coloring parameter will generate at each vertex. If coloring parameter, if I generate at each vertex, and then if I know my kind of model, it is a smooth or it is a flat model, then fragmentation can happen. So right now in Goard model we will do the all computation at vertices. So if vertices are less, then lighting will not happen that nicely. But calculation are less. In the form model, the calculation is more because per pixel wise or per fragment wise we are doing the calculation, not at the vertices. But it makes sense if vertices count are less, at that time it would be smooth. If vertices count are many, then vertices calculation is okay. Okay, so we'll see the kind of Goard model, per vertices light calculation model in shader. Further to a discussion on OpenGL shaders in lighting. So we'll proceed on desktop. Okay, we'll go point by point. So shaders is kind of same thing what we covered in fixed function pipeline. Okay, so difference is whatever the API we are using in fixed function pipelining, so nothing is there absolutely, and it is moved to shaders code. Okay, so in lighting, light happens from two mode, that is light source and material reflection. Support RGB and color index, the lighting mode, and a vertex should receive the light. That is the idea. So we are talking about Goard model right now. So in Goard model, vertex should receive the light. Okay, in the smooth per vertex calculation will happen. Otherwise, flat per primitive calculation will happen. Light source position set after. So if after view matrix, if we specify the light position, then transformation is possible. Okay, so lighting, light, material and transformation. So this computation now shifted to shaders code. Okay, so light source, if we see, then light source has properties like position, direction and color. So where light source is positioned and what is its direction and what is its color. Same for the material also, its position and its normal and the color. Okay, so light source is of two types. This is kind of for the detailed discussion, the tutorial on the fixed function pipelining that can be seen. So one is directional one and one is kind of positional one. So from the position light emits and it comes from a direction. And if I place a cone, then light becomes a kind of a cone, a spotlight. Okay, light must fall on the vertices. If light is not falling on the vertices here and there, it doesn't make any sense. Light calculation would not happen. Okay, so how, if I say fourth parameter in the light position is 0, it becomes a directional light. Directional light comes from infinite distance. Like if I say 0, 0, 1, then light is kept at 0, 0, 1. Okay, but light would come as in parallel. Whereas positional fourth parameter light position is 1, but light will be kind of omni and it is kind of emanating from this position. So directional is kind of parallel light, like sunlight. Okay, so light calculation. So light has RGB component and material. So light source emits light and material has color. Okay, so light R and material R, G, light G, material G, light B and material B, all three combined, then it becomes the kind of the each vertex light. So this is the mathematics. If multiple light source is there, then first we are done, then next we are done. So common thing is material. Okay, so if we take out kind of if we combine this, then it can be kind of LR plus LR1 plus LR2 into MR, LG1 plus LG2, like that. So this is the light calculation at each vertex. So light from the R from the light and red from the material, green from the light, green from the material, and blue from the light, blue from the material. For each light source, it is calculated like this. Okay, now the light is kind of, it has three component, ambient, diffuse and specular. For material also, it has four component, specular, diffuse, ambient and emission. Okay, so there are two entity, one is light source that emits the light and one is material which receives the light, and there is a third guy called light model. So light model is kind of, it is a, there can be many light source which emit the light, but light model will be always only one, and it has few properties, like it also add to ambience, then front side of the material and back side should be kind of lighted differently. The viewer is at infinite distance or it is near to the object, or secondary color should be calculated after the shade, after the kind of once we finish the texture. So that is the idea. Please refer a tutorial on texture in fixed function pipeline. Okay, so ambience is kind of which adds ambience. So if there is no particular light, like if someone is working in night, and then if he is kind of bringing his hand, and whatever color he is seeing, when he sees that is the kind of ambience color, because there is no light source that is falling on the hand deliberately. There can be moonlight or there are other bulbs or tube lights or whatever. So ambience is the kind of environmental light. So how much it adds to environmental light, how much it adds to diffuse. Diffuse is the actual light of the material that will fall on the material, and specular is the shining. So like that, material has diffuse component, specular component and ambience. It has emission component. So emission is kind of, if there is nothing specified, then what light it would emit, like a light source. So it won't be exactly like light source, but that is how it is. Please refer to the light model in the fixed function pipeline. Okay, so if model view is there set, then there can be transformation in light source and model. So light source translated where model is rotated. So if we specify model view matrix prior to kind of specify, so if we specify light source and model, or light source particularly after we specify the model view, then light source can also transform. That is the idea. Okay, so this is the calculation. If this is the surface like parabolic, and at a particular point, if this is the normal and this is the light falling at that point, this is the I, and V is the tangent at that vertex. If these these four kind of attributes are there, then how it is calculated? So diffuse is the material diffuse color. So light diffuse, material diffuse, they constitute the actual color of the material. So actual color is only possible if light is falling exactly upon the kind of normal at the vertex, then it will be actual kind of bright color we see. Or if light is not at coming in the direction of the normal, at least light is at the angle, then it is dot. Dot means cosine of the angle. Cosine dot is nothing but what is the component of this light along n. So L dot n means what is the component of L along n. So if light is in kind of perpendicular, then there is no diffuse color, there is no color at all, because light is color perpendicular to the vertex, means there is no color at all. Okay, so this constitute diffuse color, whereas specular will have L dot n and E dot n both. So where is the I? So if I see the color of a material, then where is L and where is N? If I see diffuse means, if I see the specular, means shining. So shining depends upon the I also. Like if L and N is perfect and I is at perpendicular direction, there won't be any shining at all. So there should be some angle between N and E, that is not 90 degree, and there should be some angle between N and L. So light direction, normal from the vertex, and I, all three. So N to E should not be 90 degree, and N to L should not be 90 degree. So L to N decide the diffuse color, and N to E and N to L, both together they decide the specular. Okay, so this is how it is. So there is a calculation, like if surface moves, it it transforms. Like surface is here. If it transform, like I have a surface called V, and it transformed by B, then how much N transform? Because calculation is happening on N, okay, not on V. So if there is a model view matrix transformed by B, then how much N transform? So N dot V. So our model view matrix and N, it's normal. If I see dot, then that is 90 degrees, so that is 0. So if in the model view matrix there is a transformation of B, okay, so B, how much there is a transformation in N, that is A, suppose, then this formula, what we showed now, it becomes like this, and finally it comes like this. So A is nothing but transpose and inverse of B. So if you see the kind of model view matrix, actual matrix, then first three row and first three column is a kind of rotation, and a right column is transformation. So inverse and transpose are same thing. So if I inverse and transpose, it is same as the model view matrix that we had in V. Okay, so but the translation differs. So whatsoever. So if I transpose, if I transform a model view matrix V by B, then its normal would transform by A, that is transpose and inverse of B. So that is the calculation. So calculation starts from here and goes like this, and then from here again like this. Okay, so for detailed explanation, please refer light calculation, light tutorial, fixed function pipelining. So this is the final calculation that we see. So light at any vertex is emission light of the material, ambient light of the light model, ambient light of the material, and then for each light source is N, for each light source its attenuation, spotlight effect, and then ambient into ambient of the material and light, diffuse and diffuse of the light and material, and shininess of the specular and shininess, specular of the light and specular of the material. And here it is S, here it is L, we described. Okay, in diffuse it is only one, L to N, whereas in the specular L to N and E to N, I to normal, both. So that becomes a surface and surface to N. So this is the net calculation of the OpenGL light and material, light component and material component and light model component, everything, how much a vertex should calculate, RGB. So that is the net calculation. So it is kind of, so first is emission of the material, an ambient light model, ambient material, and then per light source, its attenuation, spotlight effect, ambient, diffuse, and then a specular, and whatever we are getting, power to the shininess. So this much we get. Okay, so we covered this. So in the lab session we will have a kind of light source, projection type, light model, emission, ambient, diffuse, specular, spotlight. So at the beginning we'll see light source and projection type. Okay, so directional light we are using and ortho projection. So orthographic projection we are using and directional light. We can use positional light also, that we'll see. And we are using a kind of a model, and here light is rotating, model is there. Here model is rotating, light is constant, and here light is rotating, model is constant. So light is on the right direction, so we can see the shadow on the left, and light is on left direction, so it is bright. So we see kind of how transformation can happen in light and how transformation can happen in model independently. So that is the idea. So if I have a model, light moves, then I have a model where model moves. So how we can make kind of a balance between them, or how we can achieve it. Okay, so these are light model. If I don't like the light, if I switch off the light model, then how it would appear. Okay, so this one we'll see. Okay, so we start with the introduction, and then directional light, positional light, and light must fall on the vertices. Then light has RGB, similarly we have for material, and light has ambient, diffuse and a specular component. Similarly we have for model also. Emission is extra in the model, and there is a light model with kind of add ambience again. Okay, so transformation is possible in the light source also if it is declared after that model view matrix in the projection. After projection model view, if matrix is defined, then after that if I set the light source, then it is set for transformation. Okay, so calculation for the diffuse and specular. Diffuse only depend upon the light direction and normal, whereas the specular depend upon light direction, normal and the eye. Okay, if I kind of transform a model matrix, then how much normal get transformed, so that we saw. And then the final calculation of the light at each vertices. Okay, so first in the light model we'll see a kind of directional light and positional light and ortho projection right now, and we'll rotate the light and we'll rotate the model. Okay, so we can start. Okay, so we'll write the code. We'll create a directory called GL light, GLSL light. Okay, so directory is empty. Okay, so we can copy the skeleton code what we had written earlier. So okay, so this is the code. Okay, so we'll modify accordingly. So we will trim the vertex shader and we'll trim the fragment shader. So we imported glut, numpy and util-c transformation, and now we have shader program. So we'll remove this and we'll remove this. Now we have vertex shader, fragment shader, compiled shader program, and now we have VBO. Okay, nice one. So here we will place something else in the vertices, and in the normal we will place something else. Okay, now we get attrib location and then we fill the VAO. Okay, so that is the skeleton code. Okay, in the display we translate to -4 and then we'll remove everything. I think it's completely alright. So there is nothing in the code. So here we initialize the glut and we use double buffer and other stuff, and in the keyboard we use util-i keyboard and we pass the transformation, and that's it. There is nothing more. And in reshaping projection we have for this, so we'll use ortho. So instead of perspective, the way we discussed, GL ortho minus 2.5 minus 2.5 into H by W, 2.5 into H by W 1 to 10. If width is less than height, else GL, else we can copy this only. Okay, so else GL ortho minus 2 into width by height into width by height okay, so GL ortho minus 2.5 width by height, 2.5 width by height, minus 2.5, 2.5, 1 and 10. Okay, if width is greater. So this is what we are using now. Okay, now if it enters the display, then a push matrix and translate and for and GL pop matrix. So it's pretty clear. Okay, now we will use GL uniform location and print. So we have removed everything, only filling the vertex buffer array. Okay, and filling the normal vertex normal, then we'll get the location, and then here we'll fill, and then vertex location and color location. Okay, so VAO, VBO ready, and program linking is ready, and skeleton code is ready. So we need, so we will copy object loader here, and we will copy OpenGL util here. So we have this much code right now. We'll copy one object file. Okay, so we have whale shark. This is an object file generated through Blender, and it has vertices, and then it has I think vertices are too many. So this much will go in GPU buffer. Then what these are kind of vertex textures. Okay, they are again too many. And then these are vertex normal. And then at the end, so GL triangles faces are there. Okay, so that is what it is. Okay, so now we have 4 files. So we'll open our actual code again and OpenGL util C. Here we can say like from opt loader import opt file. Okay, this is to load the opt file. Now we will fill this vertex code. Uniform mat 4 projection, uniform mat 4 transpose inverse model view light. Then we have model view sphere. So I call it a sphere. Model view, I think it would be model, it will be better, or we'll leave it a sphere. So this is a kind of the actual model view sphere, model view light, but transpose and inverse we discussed. Transpose inverse model view sphere, uniform bool, we want lighting or not, attribute vec3 chord, attribute vec3 normal. Okay, varying vec4 is vertex color, and now void main vec4 color equal to vec4 01. So color is green, means we are hard coding it, color. GL position is projection into model view sphere into vec4 chord 1.0. Okay, now if we use lighting, then what would be the vertex color? Equal to what? Else the vertex color equal to color. So here all the intelligences. Okay, probably we'll develop later. That's it. So we can kind of beautify it. Okay, now here again we have varying in the fragment code, and now we have void main, and here we'll set GL frag color equal to vertex color. That's it. So this is for the lighting. Now we'll move and we'll kind of we'll finish other stuff. Now I think we have okay. So now transformation. Now we have shapes. So like I have a light source and other shape is shapes, and I have a light source, and then I just say sphere, and now this is kind of for x in shape. So this is a kind of hash dictionary, and current shape is light source. So transformation matrix is done. Okay, so here we can kind of enable the shader. So we'll say GL use program shader program, and now we'll for I in. So we have projection, then we have other big names. So or I can make 4YY or 6YY, and okay, so these locations we will know what is the location of this area. So set attr now. So we'll remember the location in this init function object only. So I'll say I plus log, set this to GL get uniform location shader program I, and just set it. So same thing we can do now here. So I can say for I in code okay, so init log and get attribute location. Okay, so set attribute location and set attribute set uniform, get uniform location, get attribute location, and set attribute as init. So we'll remember it. Now we have VAO. So here we have a mat, and now we will kind of read it. So list obj file and whale shark dot obj, what we copied, dot objects dot values, and the first object and its vertices. So mat, we are getting all the vertices. So now for each, okay, so I have 3 unit in vertices x, y, z, then 3 unit in normal, and then 2 unit in texture. So there are 3 vertices and 6 its other attributes. So 8 coordinates for 1 vertices. So that is the grammar here. So now we'll push the buffer here. So I'll say kind of buffer np array util c get buffer matrix 0 to 3. First 3 is and total length is 8. Okay, d type dot float 32. Okay, so get buffer, if I give the array and every 8 stride of 8, every 8 beginning to next 3, okay, beginning and then next 3 in 8, so that's what, so I think it's not a bad idea that we'll later print it, so kind of mat some 48 we can print beginning. Okay, now it is done. So same thing we'll set for the here also. So np array util c get buffer mat from 3 next 3 8 where d type dot float 32. Okay, so this is for a normal. So I'll read, this is normal buffer, normal buffer. Okay, now we'll get for init dot code lock. Okay, so this is the location for the coordinate, and init dot normal lock. This is what we have got here, chord and normal I underscores log. So this is what we are pushing in. Okay, we are setting its attribute, and then chord dot log init dot normal log. Okay, so it is normal buffer, so call buffer is gone. Okay, so normal buffer, and then VAO we are initializing, and two attribute array and coordinate location, normal location. In the pos buffer we are pushing at the coordinate location and normal location. Okay, so it's not a bad idea to remember few things. Set attribute init and mat and real mat, and set attribute init va opt vao and vao opt. Okay, so va opt and matrix we are remembering, probably we'll use later. Okay, so now the time has come for this mining. Okay, so what are the things that we have placed here in the kind of vertex shader? So projection, transpose, inverse, model view light, model view sphere, transpose, inverse, model view in sphere. So these are, so first projection will push, slowly we will push everything. Okay, so we are in display. So we'll push here the projection. So GL uniform matrix. So for FV. So we have already pushed attributes. So attributes are pushed at location, init, code lock and normal lock. Probably we can print all the attributes here of the init. Print init attributes for print. Okay, so kind of x 0 plus plus x1 for x in init dict okay, dot items if type of x, if not type of x equal to list. Okay, so we can just print in what are the attributes we have set in the init. So init is a function object, def init. So now we have pushed the attributes. We will push now uniform matrix for FV, and what we want to push is init dot projection lock 1 GL for one value, GL false, and now GL get float V and GL projection matrix. Okay, so GL projection matrix, whatever the GL projection matrix is, we are pushing into init projection. Okay, now this is for GL light movement. So here again, so first we will translate. So we will say GL translate x if len of x equal to 3, else GL rotate x for x in transformation light source. Okay, so at the beginning we have a transformation that is a kind of hash, that is a dictionary, and in this dictionary there is a shapes like light source and a sphere. For each we have an array. This is transformation array that will be filled in the keyboard. So once we press something, so there is a utility library and keyboard. If we pass transformation, so here we will fill more detail, then we will fill other uniform. Okay, if key equal to tab, then in this case shapes equal to shapes. Shapes dot index, whatever the index of shape is, +1, and then kind of modulo len of the shapes. Okay, so this way we increment the shape and utilize keyboard transformation of the shape. We then will print the verbose transformation. Okay, if R is search, beginning T, so this is for toggling the lighting, so that will also key decode. So key being kind of byte, so we'll convert it to kind of first string object, GL uniform 1I and init dot lit lock 1 if key equal to T, else 0. Okay, so we are done. So this is to invert the lighting. Okay, so now we'll come to our main business. So here we are rotating and then we will do transformation in the lighting. Okay, so here it is transpose inverse model view light lock. So transpose inverse model view light lock, and here we will do the inverse. So np transpose np linear algorithm dot inverse. Okay, so this is the grammar is we want inverse. I mean we have discussed it. Okay, so we have to calculate somewhere transpose and inverse. So this is what we are doing. Okay, now GL pop matrix. Okay, so we'll copy this. So we'll do same for the model. So GL translate X, GL rotate. Here I'll say sphere. And here we'll set GL model view sphere, and we don't need to do anything here. Okay, just get the model view matrix. Okay, so here also model view matrix. Okay, now here also model view matrix. Okay, now we have transpose inverse model view light, model view sphere. Model view sphere lock. Okay, so I think we have done with the code. So in the display, first we are translating to -4. We are changing model view. Okay, so probably we'll push it here only. Okay, so first we push the projection matrix to the projection location. Then we change the model view. Okay, we push again and we do some rotation in the model view. And whatever rotation we receive, the transpose and inverse of that rotation. So line algorithm ENV. So that we set in the transpose inverse model view light location. We pop the matrix. We push the matrix again. We do the transformation for the sphere. And then we set the model view sphere location and model view matrix. We set whatever transformation we do for the, here we do for light source, we do for the sphere, and GL matrix 4V, and then it is for transpose inverse model view sphere location. So this is for inverse, transpose and inverse of this model view. Okay, done. So probably we will fill this. So let's understand what's going on. Okay, so what's going on behind the scene? I mean, this is a matter of curiosity. Okay, we are not calculating a specular, we are calculating only diffuse. But we are rotating the light separately and we are rotating the model separately. That is the idea. Okay, so suppose that this is our model view matrix. Okay, so this is the model view matrix, and this is the model view matrix, and this is a normal, and this is the light, and this is the I. So I we don't care right now because we are calculating only diffuse. Okay, how we rotate the light. Okay, so In shaders programming, if we see the shader code, there is nothing light source and rotation, there is nothing like that. Vertex color, only two things we have to decide. Here, what is the position? So, what happens is, when I call display, means when display is called, and then everything, whatever it can push, whatever the data in the GPU, it can change, like it is changing init projection data, it is changing init transpose inverse view light location, it is changing model view sphere, it is changing transpose inverse model view sphere, transpose inverse model view light. And once it is done, then then we have to call the actual drawing algorithm. So we'll say GL bind vertex array and init dot we have kind of pushed it in it, and GL draw arrays, GL triangles 0, length of init mat divided by 8. That's it. So after that, when we call GL draw array, and draw array now it sees the buffer. Okay. So draw array, it sees the VBOs. So we have in VBO, we have vertex and we have normals, and that is bound to, in shader code, that is bound to coordinate and normal here. So in the VBO is a buffer that is stored in the GPU, and one by one in the GPU, one by one it starts calling. Okay, GL draw array. Okay, so in the GPU, whatever is stored, vertex and normal, one by one, so per vertex it will start calling. Okay, divide by 8, because this is how it is. So it will start calling one by one. Now I have to decide what would be the what would be the new position for it. So this code is getting called again and again each vertex in the GPU that we have stored. So for each vertex, the position is projection into model view sphere. So whatever the model we have changed, so new position of the model into code. So what is this line? What is this line? Okay. So suppose that this is okay. So this is a kind of a model. Okay, and model has a kind of a point. Model has a point. Now model is rotating. Okay, so we rotated by 45 degrees. Point change. The point location changed. I think it's quite visible. Earlier point was somewhere else. Now it changed its location. Okay, we can try again. Okay, so okay, so here it is at the beginning. Now I'll rotate by 45 degrees and it changed. What is the new location of this point? If I do some transformation, that is a big question. So that is this. Whatever transformation we have done transformation. Model view sphere, this is the model view transformation. Whatever transformation we have done, this is a 4 by 4 matrix. And this is 1 by 4, this is 4 by 4 matrix, and this is 4 by 1 vector, means matrix or vector. If I multiply this matrix, new matrix, that is the rotated one, with the old coordinate, it gives us new coordinate. Okay, so model view sphere, that is 45-degree rotated. Okay, if I multiply with the old coordinate, the result is vector of size 4, that is the new coordinate. Okay, so that is the kind of fundamental. Pretty clear. Okay, so if I translate this, again its position change. How much is change? Okay, so if this is the old position, code is the old position. If I multiply this with this transformation matrix, now I did translation, then it will bring a new location. So it will be of same size, same kind of row by column as whatever we have. So it will be kind of vector 4. It's not a matrix. And if I multiply by the new translation, it will result in vector 4 only, but new value will come. So here earlier if it was at position x, and it is now it is at position, earlier it was at position x1, now it is at x2, then this full multiplication will give x2, where this is x1. Okay, so this is matrix multiplication. Okay, so how will rotate light? So light rotation is same thing. If I have a light, okay, now suppose that I have a light, and that is at this location, light normal. Okay, light has a normal. So light normal is at this location. I think it's better to bring at them. Okay, so light normal is at this location. Now if I do translation here, then light has to move. Okay, light should move, means, okay, what I'm trying to show is that how I can move the light source. Okay, now I know that how I can move a kind of a model, how I can move a light source. So I have a kind of a model view matrix, and if model view matrix is kind of, if I am changing the model view matrix, okay, then what I need to do, that light source will come here. Okay, because light source I want to move the way model view matrix is moving. So what I need to do? Okay, how I can move light source? So the idea is that I can go for same multiplication. Model view, if it rotated, then if I multiply this model view with this light source old position, it will bring the new position. But I have to multiply with the normal. Okay, it's a normal. Okay, not the actual matrix. So I have to bring the transpose and inverse of whatever the model view, if there is a transformation of B in the model view, inverse and transpose, if I calculate, that will be, this is again a matrix. If this matrix, if I multiply with the old location of this light source, it will bring the new location of the light, the normal. Okay, so if I understand this formula, then I can calculate the vertex color. Okay, so vertex color is vec4 color.rgb into dot normalize transpose inverse model view sphere into vec for normal 1.0 dot xyz normalize transpose inverse model view light into vec4, okay, and then 0 0 0 0 x y z color dot e. Okay, so if I have a vertex normal is this, how much normal would move if I move the model view sphere? Okay, it will move transpose inverse model view sphere into vertex normal. Okay, now we calculate x, y, z and we normalize it. Same way, transpose inverse model view light, and this is the light position original 0, 0 and 10 in the kind of that direction. This is 0 means directional light, and now x, y, z and we normalize it, and finally we do the dot these two. So two normals we are doing dot. This is what we are doing. Okay, one is light normal, okay, one is light and one is a normal. Okay, so we are doing actually this a dot n and b dot v. So okay, so we are calculating this diffuse. So light normal and vertex normal. Okay, this is vertex normal, but due to transformation matrix this normal is changed to this much. Now this is our light normal. Due to transformation matrix this change this much. Okay, that is the new vertex. Okay, so this is the way vertex color is changing. So if I see this, we go to the previous location. Okay, and if there is a vertex, okay, so if there is a, what would be the vertex color here? If light is falling here and model is rotating, so right now the light is falling on the vertex but model rotated. Okay, now light is not kind of straight there, so this normal is this, normal is in this direction, light is falling in this direction. So this is the theta, the angle that we have to calculate the dot. So light angle and its new normal angle. So the new normal is this, normal into transpose matrix. So light we are not changing, light location is same. So certainly this color would fade because it is going in the angle of the light. Okay, now this is fixed. What about if I move the light? Okay, I move the light here, then again it will fade more. Okay, the angle is growing, so cos theta is less. So if normal is fixed, now we are not changing the normal, but like inverse transpose inverse model with light is changing. So this is becoming lesser. If this is becoming lesser, I mean this is going away, then this dot what we are calculating dot, so dot will be smaller. So vertex color will be fade, it will be less. Okay, so this way, so we can try executing it. So we will go by the code what we have done probably. Okay, so we have numpy array, object loader and util-c, and light source and sphere is there. Current shape is light source, transformation matrix is ready, and here we have uniform matrix 4, projection, transpose in model light, sphere, and lit, and coordinate normal, varying is vertex color. Color we have fixed as green, and then position would change. The way model view sphere is changing, there is no transpose inverse here because it is not normal, it is a simple coordinate, we are modifying it. And then vertex color would change the way we change the transformation, we change the model view sphere and we change the model view light, and that's it. And then varying vertex color, the frag color is that much. Now we compile it and we use it. Now we get the position of projects, all these uniforms and attributes. Then we have a matrix of our object file, and then we set up VAO, VAO1, VAO2, and after setting up, we set the VAO, okay, and then we remember the matrix and VAO option. We print it, then we go to display. First we push the projection, and then we do the transformation as the light source, and whatever the model view matrix is, we do the inverse and we set it here. Then we pop the matrix and push again for the transformation in the sphere, and then we set the model view matrix in the model view sphere, okay, after the transformation, and then we set the model view matrix, transpose and inversed, that is in the view, okay. Then we bind vertex array, we draw it and pop it and pop, that's it. Okay, so hope for the best. Okay, something unmatched. Location, GL floor. Okay, we'll try again. Okay, expected end of the file, fragment shader, line number 6. Okay, again in the fragment shader, expected end of the line. So this is the end of the file. Vertex shader, main else. So this is main, and here I think that is all, we don't need this. So this is the main, that is the end. If not, we will get program IB shader program link status, print error, GL get shader info log shader program equal to. Okay, so probably we have done something here. Version bearing main GL pack color vertex color. Okay, so probably there is a semicolon here we have missed. We have not printed error or error. Okay. Vertex shader. Okay. Okay, GL get buffer data NP array util C get buffer mat. Did you mean type? Okay, so this is matrix we are talking about. So first 3 is vertex, next 3 is normal, and next 2 is texture. Again 3. So there are in 8 combination things are there. 25. GL buffer data NP array util C. Okay, so D type equal to NP dot float 32. D type equal to NP dot float 32. Okay, so this is probably string. Oh, so we are getting. So this is the light. Okay, but no light calculation. Shape is referenced before assignment. Okay, so global transformation shape and shape. Okay, and lit location we have set already. No? Okay, so we'll set at the beginning only, it should be lighted. Or okay, so we'll set it the way it is. Okay, so I'll press T, it will light, not light. Okay, so there is something called import RE, regular expression. Lit lock. So we will do the kind of litting at the beginning only. So here in the code, after doing all the operation, so I'll say that lit is 1 at the beginning only. So we won't print the mat. We are still printing the mat. Mat. Okay, so for X in X init dict items, if not type of X equal to list, for those only. If not type of X 0. Okay. If not type of, so this is value. Okay, so we are getting it. So this is kind of, now if I press V, there are two shapes. So if I press V, it will print that. Oh. So here I can print the shapes also. So what is the current shape? And what is the transformation? Okay, so now if I press V, so these are the locations it printed. Lit location is 4, 3, 2, 1, 0 and coordinate is 0 and normal is 1, V of is 1. Now current focus is on light source. So I'll try to rotate the light source. Okay, so I'll press Y. Now the transformation is 90 and Y axis. So light went on right side and it became dark kind of. Okay. Now I press tab and focus is now a sphere. So now a sphere matrix would move. So if I press Y, then now right side light is there. Okay. I can kind of okay, so light is on right direction. Now the focus is on sphere. So this is a transformation matrix. For light source, it is 90 degree it is rotated, whereas sphere has done this much. Okay, now we'll rotate the, so I'll press tab, now focus is on light source, we'll rotate the light. Now light went completely back. Okay. If I print, then it is 270 degree. So it came on the left side. Now I can rotate the fish. Light is on left side. It can be seen. Okay. Now I'll press tab again, and if I press V, then now I'm at light source. So whatever I do, I'll rotate the light source. I'll rotate again the light source. If I press V, 350 degree, one more time. Okay, so light 360 degree. So light has come in the kind of in the positive Z direction completely. I can rotate the light again. I can rotate light in the Y direction I was rotating. I can rotate in X direction. Light is going down, but model is not moving. Okay, now if I printed it, then 100 degree it has rotated. So minus X 90 degree. So X has rotated 90 degree and Y is 360 degree. So light is down. Okay, now if I rotate this guy, light is below the scenery. Okay, I can bring the light up. if I press V, okay, light is, X is 0. Now if I keep pressing X, it will go up. Minus 70 degree. Minus 90 degree X direction and 360 in Y direction. So light is exactly above. So if I rotate it, light is above it. So down the line it is dark. Okay, so this phenomenon we can see in the sphere also. So here whale, okay, shark object. So I can change it to kind of a sphere. I have a sphere of, so I'll copy it. So I'll try again. Okay, now I am in light source mode and there is nothing in the transformation matrices. Now I can move the light. Okay, so it will be kind of more clear if I make kind of GL clear color as kind of some essence will give like a blue. Okay, so it will be more clear. Now I can move the light. Only light is moving. Okay, now I can move the sphere now, but light will. Sphere is actually rotating. We can't see, so I can translate it. Light is there only. I can rotate, but I can translating. I can rotate, but it is not visible. Okay, now I can rotate the light in X direction. Okay, so transformation matrix is crossing the okay, so we'll make little bigger. So here we set 1 to 10, we can set 1 to 20 somewhere. And here at the beginning we'll set it to some 10. Okay, and now I can rotate the light in X direction. Okay, so this is a fixed coordinate and this is grand coordinate. This is what we want. Okay, and in Y direction we can translate the way we want. Okay, so we can bring in the whale again. Whale, shark, and we can see kind of ocean kind of, this is the whale shark, and we can rotate the light and we can rotate the shark in the light. Okay, so it's time to rotate the light. And Mr. Sark is busy. Now light is not rotating, but the Sark is rotating. Okay, so we'll kind of see the lighting enable and disable. So we have this file. So keyboard, if I press T, then kind of it will switch the lighting. So that feature we'll see. Okay, so by default lighting is enabled. Okay, so by default we had set in the init only, lighting is enabled, but in keyboard function we can change it. Okay, so by default lighting is enabled. So lighting is coming from +Z direction. Okay, so this is the position. Now I'll press T. Okay, so I'm pressing T. So small t is for enabling the light, capital T is for disabling the light. So this is light is disabled. Lighting is disabled. This is what we are kind of seeing here. So in this diagram the light is from right side, this diagram light is from left side. And if we disable the light at all, okay, whatever color we are just passing. So if I see the program, so in the shaders code, we have if lighting is disabled, if lighting is not there, then we just pass the color, whatever the green color is. Okay, so this is what we want. Okay, so I shall kind of okay, so I'll disable the lighting, so I'll press capital T and light is not there. Now I have the transformation. I have the transformation, but lighting is not there. So if I go to light mode also, Okay, now the mode is light source, and rotate the light. Whatever I do, I am pressing X, Y, Z to rotate the light, nothing is happening. Okay, so in sphere mode, though I can do all the transformations. Okay, so if I press the small t, then lighting would appear. So this is the position of the light. So probably light is coming from the right direction. Okay, I'll see where I am. So it is sphere mode. So I will press tab, and then I can rotate the light. Okay, this is how it is. Okay, so this is again I can press, if I press capital T, light is gone. Light comes. So this is about the lighting. I can change the color also. So color whatever we had taken, so it is kind of initially green. So I can make it yellow. Okay. So the shark is yellow. We saw directional light. I mean, the light which has no position, it only has direction, like sunlight. I mean, sun never knows that who is placed where. So it just emits the light, it just throws the light. So when we do the lighting calculation for the directional light, we only see the direction. If I say Z is 1 and X, Y is 0, then it is from direction Z. Okay, Z is 1 or 10 or 100, 1000 doesn't matter. So that is directional light. We can rotate directional light. I mean, it is X0, Y0, Z1.1, and now it is X1.1, Y0, and Z1.1. X1.0, Y0, and Z1.0. So it turned the direction. It turned the direction, but still distance doesn't matter. From that direction, light is coming. So directional lighting we saw, movement of the lighting, that also we saw. Projection matrix, that in projection matrix orthogonal projection. So that we saw, and we saw the kind of a specular coloring. So, specular reflection from the material point of view. So, that way. What about positional light? A light has position rather than direction. Anyway, light will have a direction, but it has position also. How position matters? Like, if I have a vertex, then earlier I was just, if I am considering the specular component at any vertex, like in kind of in fragment shader, fragment color is assigned per vertex. In per pixel, but it is decided like we set the kind of color at the vertices level only in the vertex shader. With that, with the vertices rasterization happen, and whatever the color at vertices and whatever the shading model is, fragment shader thinks about the fragmentation. So we decide the coloring at the vertices in the vertex. When we decide for the coloring in the positional line, so if I just talk about the specular one, then I have the normal vertex, normal normal vector. So I'm talking about each vertex. So when I am thinking about coloring each vertex, then normal from the vertex matters and another vertex matter from vertex position to the light position. There is also one vector passes. That is the light vector. Light vector, earlier light vector was directional. It was coming in a direction. Doesn't matter where the vertex is. It is coming from like sun is a directional light source. It doesn't know where the vertex is. So it only comes in a direction. So when we are talking about the direction, then direction of the light means the light direction with the normal to the vertices, both we are doing the dot. Now normal from the vertex, okay, anyway it is there, and the line from the vertex to the light position, that line crosses, that is the light vertex, that is the light vector. So new light vector, earlier light vector was decided. Now light vector could change the kind of orientation in rotation format, but now also it can change. But the actual line vector is wherever the light position is there. So from the vertex point, for each vertex, when we are talking about coloring at each vertex, from the vertex point to the light point, if I draw a vector, so that is the vector. So that vector and the vertex normal vector, that will do the dot, and then we'll decide of the kind of coloring at the vertex. So that we'll see. We'll see perspective projection. So perspective projection now kind of it can sense the depth. We'll see ambience. We'll see specular. We'll see shining. So we'll see positional light. We'll see kind of perspective, and we'll see the rest of the component of the lighting. We talked light now. We talked about the kind of specular reflection. Now we'll see other reflections like now we talked about diffuse reflection. So after diffuse, now we'll talk about the specular, shininess, ambience. Okay, so these three things that we'll consider. So if I talk about specular, a specular means kind of shininess. Diffuse means the coloring. So the shininess reflection. So it matters between two dots. Okay, the way we discussed. So it matters between two dots. One dot, vertex normal to the light vector. One dot. And another dot between I vector. Okay, I vector to the normal. So, or rather I can say that it depends upon the I vector and the kind of light reflection. So we'll see that. So computation is more. We are kind of pointing towards two dots. One dot we have seen in diffusive. One more dot will come into the picture. So that we'll see. Okay, so we covered directional light and ortho projection. So we'll proceed for the projection type and the light source type. So light source type we have. So in light source type we focused on directional light. So next we'll focus on positional light. Okay, so positional light where light doesn't have any direction. So light matters where it is positioned. So that is positional light. Like if light is near to the model, then only nearby it illuminates. If it comes far from the model, then full model illuminates. Okay, So like if light is here, but still as per the distance the area is illuminated, this area is not. So it is different from directional light. Okay, so directional light comes from infinite distance, whereas light positional light has a position. Okay, so position light has a position. So if I see this diagram, okay, so suppose that so this is L is light direction. The light from is a right now. So suppose that light is here. Okay, so light is here. If light is here, then light falls on the vertex. Vertex has normal. Then what about, so this point is we are calculating what would be color at this point. Okay, if light is parallel, then what about the color at this point? Still light will come in this direction if it is a directional light. If it is a directional light, light will come from this direction only. So light vector is not changing. Okay, normal would change. Here the normal is like this, and here probably normal would be like this. Okay, so when we calculate the diffuse, then this angle we are calculating. Now while calculating the diffuse, this angle will calculate. Okay, this angle. So this is directional light. But when we talk about the positional light, so light is positioned at that location only. So the light direction is this. And normal is, light direction is this. Okay, whereas normal light direction is this. Okay, so whereas normal is this. Okay, so it is different. Earlier light direction was this in parallel. So light direction changed now from this to this. So now what is the light direction now? So wherever it is positioned, the vertex where it is after model view matrix rotation, and wherever the light is, if I differentiate this, then this will give the direction of this vector. If I differentiate L minus the current, okay, so L minus the current position, so this will give the light normal. Okay, we don't need a kind of transpose and inverse or whatsoever. We are getting in this fashion only. So this is new light normal, new light vector. Okay, if it was a directional light, then light vector was this. Okay, now light vector is this. Surface normal will not change, but this angle we would have bothered this angle. we would have bothered this angle. Okay. Now we will bother this angle. So this is the computation difference between the positional light and directional light. Okay. So this is directional light, this is positional light. Probably we can save it. Okay, so I can insert that. Okay, so this calculation that we will bother now. Okay, so L is changing. Okay, in diffuse calculation. So L is changing. N will be the way it is. Okay, so we'll use positional light and then perspective projection also we'll add to the code. So where we were, so we'll start from there. Okay, so this is the code. Now we'll modify this code. Okay, so vertex color will change now. So this is old vertex color. So new vertex color. So RGB dot normalize model views for this won't change. Okay, this guy will change. What it will change, that will show. Okay, so model view light. Model view light. How much light is changing if I am rotating the light? So light position we are hard coding as 10. Probably I'll change it to 5 because I'll change the kind of perspective. So looking at its distance. Okay, so it is 5 now. So this is 5. This distance is 5. In Z direction. Okay. So model view light minus vec minus model view sphere into whatever the vec for how much coordinate has moved by then. Okay, so that's it. Okay, so now rather than going for fixed, here what we were doing was we had a fixed direction, this is directional light, and we were rotating the directional light through transform because it's a normal, it's a normal surface kind of. It's not there are two kind of coordinate. One is on the surface coordinates. If I have a model on the surface of model, there are points, or if there is something that is normal. So if I want to translate, if I want to transpose, if I want to kind of doing transformation on the normal, then I have to go with transpose inverse. If I have to do transformation on the surface, any point on the surface, then we will go with the normal model view matrix without transpose and inverse. So suppose that this is the light this is somewhere in the surface, there is nothing like normal. Then we will modify the new location like this. Okay, now it is 1 as we want the calculation to happen. So fourth parameter is the W parameter, and it gives importance, it comes into importance when we do matrix multiplication from the model view matrix. So it is 1, anyway it is 1 for the positional light in the fixed function pipeline, minus model view sphere into whatever coordinate it is moving. Okay, so it is called I coordinate. So this is called object coordinate. If I multiply by model view light, so this is the new transformed coordinate, it is called I coordinate. So this is another transform. So for the light position that I have made it fixed, this is the new transform position, and the whatever coordinate we are receiving, so coordinate means each coordinate this vertex shader is getting called. So that much. Now we do the calculation and then XYZ and we normalize. That's it. And now we'll move to, so these are the codes that we have written. Now we'll move to reshape, and then probably it's time to go for GLU perspective. And we will make somewhere like, okay, 0.5 is okay, to 20. It will be big, or we'll leave it 10, then okay, fine. Okay, we'll see. Okay, if required we'll do, and this translate we will do -5, so it will come in the middle. Earlier we were using 1 to 20. Let's make it 1 to 20 so that it will be same as what we did. Okay, and we will translate it to -5, so we'll make it same as -10. So it is going -10. Okay, light is at the 5, so it is 5 before the new origin. So new origin is shifted to -10, and whatever the new origin is, from there it is 5 in the Z direction. That's it. Okay, so it will be it will be shown. Okay, so we can try. Item 3 is okay, so there is no model view matrix, model view light, the way we stated. Okay, so we will comment this, and instead of that, now we have another matrix called model view light and transpose light. So transpose light here we had, so we will comment this, and we will have model view light. Okay, now we have this, okay, so light calculation, so we just comment this, and now we have model view light. If it is that, then we don't need these calculations. Okay, pretty straightforward. Okay. Okay, now these attributes are also looks good, and now I can place it near. So I'll press, so light source is at 5 distance, so I have placed it will go near. Okay, it came near. So this will not happen in the directional light, means either it cannot move directional light, it will change the direction in angular fashion, but it is at infinite distance. You cannot move sun. Okay, it will always be at infinite distance. but positional light we are moving, and light went inside the model. Okay, now light will come out. Okay, now so light is changing its position. Light can go right. Light went to right. Light can go left. Light went to left. Okay, so I can print the situation. So it is -1 and 0.6. So I'll press right, so it will come to kind of 0.6 still. Okay, idea is that, okay, so it went too much right. It's pretty well. Now I can rotate the light. Okay, so it is 160°. Light went behind. So now if I rotate the model, there won't be any light at all because light is backside. Okay, I'll change the light. Okay, what is its position? So light is at 200°. Oh, sorry, light was at 310, now 380. So light is kind of 360° it moves. So light is at front. Okay, so this is the positional light and perspective position. If it is a perspective position, then if I press far, it will go behind. So okay, so it should go behind. So it is going in that direction. Okay, so probably we will rotate little bit. Okay, so it is going behind. Now it is cutting the now I can bring in front. This is perfect, and it is going behind. It went out of the projection matrix. So this is the magic of okay, so why? So we'll do one thing. I mean, light is not pretty clear where we are pressing and where the light is going. So no one. So I think image is there. So we'll leave it. Oh, okay. So we'll have to cancel it. Okay. So now we'll add a kind of a light source so that it will be visible. Okay. To add a light source, we need to have a kind of another shader code. So we'll copy here. So frag shader, frag code, vertex code. So I'll say word code equal to till here word code equal to, okay, so probably we'll copy paste 42 and 14. Okay, so 14 to 42. Okay, so it can. Okay, so now we are moving towards having another vertex shader so that we can show the light. So this is vertex shader 2. Now we have projection 2. Okay, so we have model view light. So that is 2. We have coordinate, that is 2. Okay, varying vertex color, so it is internal, doesn't matter. Now we have okay, so color is, will make it 1, it will be completely white. GL position is projection 2 multiplied by light 2 and coordinate is 2. I can give code only, light only, doesn't matter, but it will be easy in remembering in the kind of init object the what we did, and that's it. And vertex color equal to color. So GL position is projection 2, model view light 2 and code 2. Okay, and fragment color is same, so fragment code is 2. Now we'll have a light source, okay, in white color. That is the idea. So this code will also duplicate up to here. $68, 85. Okay, so I'll say 68 to 85. Okay, now we have kind of another set. Okay, so this is all right. What is coded 2 and fragment code 2. Okay, and then shader program 2, and attach, so no problem, link to shader program 2, shader program 2. Okay, so GL use, so we will leave it here only. Okay, so probably we can remove this from here. Okay, so now we have shader 2 program and shader 2. Okay, so we will do it again for YY. So for this only I was setting as 2. Now it is projection 2, model view light 2. Okay, and we'll set attribute like this only. Here it will be in shader program 2, and here it will be in shader program 2. So it is called 2. Now we set this also. Okay, now we will have buffer of 2. Sorry, so here a mat. Okay, fine, no issues. Okay, so we'll have one more buffer. So VB01, VB02. So here one more have VB01. So idea is that in future we'll place this in some library code so that it will be easy to call. So pause buffer. Okay, so probably we'll do after we do everything. So we'll remove this for the time being. So let it be the way it was. And now vertex array 2, and it is 0. VA opt, and here we are letting it to 1, so that we will see later. So this is the code for the VA of 0, and we are setting everything. So done. Now we'll copy this. So VB 0. Okay, so 1 pos array nice. Okay, and we will have another called mat2. So mat2. Okay, so we will, so here opt file is whaleshark.opt. Now we'll have kind of q.opt. Okay, and there will be q and bb gen buffer 1 pos buffer, and then we'll get mat2. Okay, now we'll copy this to yy. Now GL bind vertex array 1, and in that attrib pointer is called toLock. Okay, vertex attrib point init called toLock, and here it is pos buffer. Okay, so pos buffer we initialized, and GL buffer data we pushed. You will see mat2 and 3 to 8 only vertices, and then we create GL bind vertex array 1, enable. Okay, GL enable vertex log 2, and then attrib pointer log 2, and then okay, so this we don't need. GL buffer pos buffer we have done. No. Probably it will come here. Okay, so GL enable vertex attrib array log, GL bind buffer pos buffer, whatever we created. Okay, and GL vertex attrib pointer. Okay, so I think this looks well. Okay, so now here temporarily I'll say GL use. Okay, shader program. So GL use program shader program, and initially we'll set the lighting to 1. Okay, so lighting is not disabled. Now it's time to set these variables. Okay, so VA opt is set, mat is set. So we'll set mat 2 now, because now we have 2 vertex and fragment shader. Okay, we'll set shader program, and we'll set shader program 2 so that we can use it later. Okay, and we'll have another attribute. We want to display the cube or no. So init cube. So initially we won't display the cube. Okay, we can place it here. it will be cleaner, I believe. Okay, now use shader program and that's it. Okay, so probably we are done and we'll come to display. So nothing need to be touched. So everything will move the way it is. Here we'll say GL use program init.shader program. Okay, now everything is done. Now it's time to use another code that we have written for cube. Okay, so if init.cube, if that is the case, then GL use program init.shader program to GL push matrix. Okay, so we'll copy this and we'll proceed with the same translation for the light source because it will move the way the light source is, and we'll position GL translate 005. This is what we did in 0. So light position is set as 0005. So same thing we are doing. Okay, now we'll copy projection here and we'll copy mode lighting here. So projection will copy here. So projection, the code what we had done. Okay, probably I think it won't change, so we can copy it here only, projection 2 and same projection, whereas this model view light, so this will copy init Q, GL uniform matrix 4B and init model view light 2 lock, okay, and model view matrix. That's it. GL bind vertex array init.va obj1 and GL draw array GL triangles. Okay. 0 len init mat2 by 8. Okay, so now here we did binding for VA obs, so it will be 0 and VA ob it will be 1. So we can do GL pop matrix. Okay, so now for the cube GL use shader program 2 push matrix, do the translation in for the light source, translate to 5 and then push model view light 2 lock and then just do the drawing. That's it. Now here in the keyboard, okay, so cube will set reset in the keyboard. So I think for the cube we can make CC. So if it is C, key decode. Okay, so set attribute. Okay, in the init for the cube it will be 1 if key equal to C is 0. Okay, so it is completely done. Okay, so no one stops us trying our luck. Python FGL light cube object is not there, so we'll copy temp image globe as cube object. We'll try again. Okay, invalid value code 2 is not there. Now we have word 2. Inside that we have attribute code 2. Okay, normal is not required. So attribute code 2 varying vertex and color and code 2. Fragment code 2. Now we have word shader again. Okay, and here we are shading word code 2, word shader, frag code 2, frag shader, and now shader program 2, GL attach shader program 2, link shader program 2. Okay, now here projection 2, model view light 2, shader program 2, we are setting, getting attribute location for the code 2, we are getting the attribute location and setting in the init. Okay, so we'll try luck again. Oh, it is coming. Okay, now I'll press C and let's see if cube appears. Okay, I am pressing C, but cube is not appearing. Oh, appearing. Good. And it should vanish. Vanishing, appearing. So, cube is appearing. Now, light source we can see where it is. So, I can rotate the light source. Okay. Now, light source is visible where it is. Okay. I can take light source left. Okay. I can take it right. Okay. Now, this light source I'll make it go near to the object and it is diminishing, light source went inside. Okay, so light source would come now out. Okay. Okay, so there is nothing much informative. So we just did so that light, we don't know where the light is. So positional light, it really matters. Okay, so if it goes near to the model, then, so this we cannot see in the directional light. Okay, so that is the phenomenon. Okay, now full light. Okay, and I can rotate. Okay, so should appear bigger, and if I send it, it will keep appearing smaller and smaller. So this is perspective projection. Okay, so this is how it is. Okay, because we change this transformation axis, so we'll make it right. So it should be better. It is perfect. Okay, so we'll move to the next topic. Okay, ambience, diffuse and specular. So this is, if we see little closely, then there is a red spot. So this is specular, it's shining. We can move the red spot. Okay, because light has moved, so red spot has moved. This what we are seeing at the back side, this is ambience. Okay, so no much engineering is required. Shader programming is kind of it takes care of many things. We just need to add it in shaders. That's it. Okay, otherwise in the fixed function pipelining, kind of we would have to do much more thing. Okay, now we'll open this file. Okay, so we'll comment it again. We'll rename this color to kind of diffuse color. Okay, we'll make it 1. Okay, shining will come perfect. What else color we need to add? And here we'll make specular color. Specular color. Okay, so that is red, and a specular exponent equal to 10. So we are slowly moving towards the net light calculation. Okay, here whatever we have, the net surface normal in powers to the shininess, specular light, specular material. So specular light we are not mentioning. Okay, so here I can mention whatsoever come to my mind. So diffuse is L dot N that we have seen. Now specular is L dot N plus E dot N. E dot N, this is N and this is E. Okay. Okay, so we'll write the code. Vec 3 NLRV. Okay, so we'll see what is NLRV. So V is E here. Okay, so probably I'll make it E. Okay, so normal is whatever we have calculated. Okay, so that is normalize model view. I think it's not bad idea to copy paste. Means it is understandable what we are doing. So this only we will just copy paste. Normalize up to here. Because this is same. Okay. Then we have L equal to normalize and vec 5 minus, so it is same. So this for diffusive component n into L, that we have anyway done here. Okay. Now we have E equal to this we are adding. Normalize. Okay. We are considering at 0, 0 position. Okay. So vec 3, 0, 0. Where is I? So I is considered at a fixed location. Okay. So I can say vec 3, 0, 0 minus. So I am considering I. It is okay. I is pointing here. So I is in the transformation. I is at 0, 0, 0. This is kind of in projection matrix. This is what we consider for perspective projection. So vec 0, 0, 0. I mean, it can be changed. Like I is here somewhere. I can change it. Where is my I? So I am considering at 0, 0, 0. Okay. So that would come to model view sphere into vec 4. So I would move chord 1.0. Okay. So I position to the wherever is my coordinate dot x, y, z. Okay. So here light position wherever I am drawing it, and here I position and wherever I am drawing it. So this vector. Okay. So this will become a net vector as I vector. So vector 0, 0, 0 minus model view sphere. Okay. And a vector coordinate x, y, z. Okay. Now we'll do the computation. If dot L dot n less than equal to 0.0 means it is backside. Okay, if that is the case, then vertex color equal to, okay, so this is ambience 0.5 and 1. Okay, 0.05. So it is 2 less blue. Else, okay, so probably we are inside something, so we'll do. Okay. Else vec 3 color equal to 0.8 into dot L dot n into diffuse color dot RGB. If dot R, okay, okay, so now we are calculating the second part. L dot n we did and E dot n that we are doing. So E is E Okay, so okay, so L dot E, okay, so L dot E into diffuse color dot RGB. Okay, so we are in if statement. So if dot L dot E vec3 color if dot R dot E greater than 0, color plus equal to 0.4 into power dot. Okay, so L dot E specular exponent into specular color dot R. Okay, now vertex color equal to vec4 color. Okay, diffuse color dot A. Okay, so finally we are done. It was little complex. Okay, now we have NLR. So R we are not calculating. There is something R. So I'll just leave it. So N, L and E, the way we promised. So N and L anyway it is called calculated. E is from 0, 0, that is the I position, minus model view sphere, the where the coordinate is rotating. So that we normalize. Okay, if L dot N is less than 0, means we are at kind of wrong side. In that case, only show the ambience. Okay. Else we have a color. So for diffuse 0.8 dot L dot N and diffuse color dot RGB. Now we are in another business E dot N. So L dot so N dot E. Okay, E dot N or N dot E. So dot N dot E greater than 0, then color plus equal to power dot N dot E into a specular exponent, that is 10, and a specular color dot RGB, and vertex color equal to color. Okay, so we have set exponent as 10. So I believe we are done. Okay, so we have done all the calculation the way we said. Okay, it is both we have to add, and then so we are not adding straightforward. It is because it is 0.8 and it is 0.4 and power. So this is the actual calculation. Okay, so N dot E, this is okay. So we'll try specular component, specular color, diffuse color. Okay, so there is error. L less than equal to 0, less than equal to 0, then vertex color equal to. Okay, so normalize sphere into dot xyz. This is perfect. Okay, so model view sphere, whatever come xyz, and then decrement it, and then do the, or we can just remove it for time being, just minus. Okay. Okay, so dot take comma. So try again. Comma. Color undeclared. Okay, so here it is diffuse color. Okay. Okay, so at the beginning only we got the result. So we can see kind of okay, so shining is there. Red color shining, this is what we wanted. So I shall place the Q. Okay, so this is what we were looking for. So this is red color shine. Probably this will be more clear if we use the sphere. So here I'll change it to sphere. It's there. Okay, so red color spot can be seen. Okay, now I can rotate the light. Okay, one demerit is there. The shining part, it is not rotating the way we want. Okay, so that is the problem we are seeing. Otherwise it is okay, all right. Okay, so we'll change this to kind of okay, so we'll introduce a new thing that is called reflection. Okay, so we'll use now, there is something called reflection, and this is R. Now, reflection, if light is moving, then reflection would also move. Okay, otherwise, normal, okay, So the way, otherwise it's fine, means whatever we are doing the calculation, it's okay. But if light is moving, we are not able to use it correctly. So we'll use another guy called reflection. So we'll have now R. Okay. Now reflection will have its own calculation. There is a ready-made built function reflect. Okay. So light to the normal, we will use reflection, and this n will be replaced by R, and this n will be replaced by R. So now we'll try again. So Ln for diffuse color, whereas R and E for a specular color. So we'll try again. Okay. Now we'll rotate the light. So I'll bring the light cube and we'll rotate the light. It is rotating. Since light is rotating, its reflection is rotating, we change the vector. Okay. Now I can change the color of the specular. So specular color is red. Okay, let it, and diffuse color will change, so we'll make it green the way it is. Okay, so diffuse color change, and red is not very prominent. Okay, so this is how it is. So sphere can move up. Okay, so light is shining is going down because it is moving up. Shining went to right side. Okay. I can rotate the light. Okay, so clearly it is shining. Shining color we can change. So shining color is red. We'll make it kind of this color. Okay, it is prominent, looks like white. Okay, so if I keep it as diffuse color as white only and this color as red, and we'll bring back our shark, Mr. Shark. Okay. I'll make GL clear color as black only. Now we'll rotate this. We're rotating the light. Whereas I want this. This is blue. Okay, so probably I'll rotate the light. This is blue. This is ambience. I mean, I can make it even prominent. Okay, so probably I'll make it 0.9, 0.8, it will be prominent. Okay, now I'll rotate the light. This is blue, this is not black. I mean, I can make it more prominent. So probably I'll make it 0.2. And light comes. This is okay. So this is ambience. If light is not there, still we can see the color. Okay, so this is ambience. If light comes in, now we can clearly see the ambience, and if light comes in, then we can see the red color shining. So that is the specular. Okay. So as per the lab exercise, so in Earth we can see the backside as ambience. So I'll bring that. And here, as per the exercise, it is black. The diffuse color is green. Okay, so I have light, and I'll rotate the light. This is ambience, the blue color, and right is rotating, and we can see the shininess, and so green color is specular. So this is ambience. Green color is specular, and what red shininess, that is we are seeing. The green color is diffuse, and red color is specular. Okay, this is perspective projection, so okay, this is how it is. Lighting model in OpenGL. So far we have seen the lighting calculation through shaders program, and in the shaders we have calculated diffuse color. Okay, so we also saw that when we calculate the I coordinate, or we do the transformation of the kind of transformed coordinates, means transformation of the coordinates, then two kind of matrix comes into the picture. If kind of vertex is lying on the model surface, then we go through model view matrix. If vertex lies on the surface that is normal to the kind of the model, so we call it kind of normal vector, or then transpose and inverse matrix comes into the picture. So we saw the kind of model transformation, light source transformation. Light source type as directional and positional. So in the directional light source, we just bother about the direction of the light, so normal vector. Where in the positional light source, we bother the position of the light and the transform or the vertex position in I coordinate, that is the transformed vertex position in the I coordinate. So that we saw where so in the diffuse, while calculating the diffuse color or diffuse reflection from the material, then light vector, I would say light vector, and normal vector, everything transformed. So normal vector transformed and light vector transformed. If it is a directional light, then light vector transformed. If it is a positional light, then light vector is kind of it is calculated through light position and the new position, transformed position of the vertex. So so we calculated the diffuse color when we were rotating the model, when we were rotating the light source. So that we saw. Then we calculated ambience, we calculated kind of a specular, we calculated a shininess. So whatever we have achieved by now, so everything is vertex calculation. So we calculate all the vertex transformation, transformed vertices, coordinate, and its attributes like normal or lighting parameter, everything per vertex. So there is a problem in the vertex. What about, like I have a sphere and the number of coordinates are in thousands? No problem. Means vertices are so near to each other. It is so densely packed. So doesn't matter much. But what about where vertices are far away from each other? So one primitive, like if I say triangle, it has a kind of meaningful surface. So number of vertices are less. At that time, lighting would not be perfect. Means it will see means how it performs when we have kind of a sparse vertices. So calculating all the light parameters on vertex wise, then it is not a very wide step. Means the lighting will be kind of, it will be scattered. It won't be kind of the real world lighting and shining and more about it. So what is the solution? So this whatever we have done, it's called GOAD model, per vertex calculation model. So if I want that lighting should be calculated separately at each point in the kind of model. So if we call it at each fragment or loosely at each pixels. Okay. So if I want that, then I have to do calculation per pixel wise or per fragment wise. Okay. So what is the problem here? Problem is too much. Means I have 50 vertices, but number of the pixels may go in kind of hundreds or in thousands. So that much calculation per transformation. So what we need to do now is that we have to take out all the code what we calculated, light normal and vertex normal, transform light normal, vertex normal, and I normal and reflection of the light while calculating the diffuse ambience and specular color, shininess. So everything now will bring it to fragment shader. This is called Phong model. So in Phong model, we will calculate everything per pixel wise, per fragment wise. So number of calculation is very high. But okay, we'll get the smooth result as far as lighting is concerned. So from the vertex shader, since transformation is the responsibility of the vertex shader, so everything transforms, everything vertex to normal, everything transforms, in I coordinate. So that we'll get, and our calculation we will do in the fragment shader, means normal estimation will happen for the pixel and other estimation it will happen pixel wise. So that is the calculation. So that we'll see that how much more computation equals. So we can think about it like if I do the pixel-wise computation. The only thing that makes sense pixel-wise computation is texturing. So since we have an image, I have an image is pixel-wise, so it may loosely map to per pixel. So anyway, I have the data available. So through sampler, I can just get the per pixel data and just change the color of the pixel. But if I have a primitive and then I have 3 vertices and where all the attributes are set per vertices, means even though I do the transformation and get all the attributes in I coordinate or in a transformed coordinate, but still getting things per pixel wise and then doing the calculation. So that we'll see. So Phong model is costly as per calculation is concerned. So if our hardware supports that much calculation, then we can achieve that. In addition to that, we'll also see kind of spotlight. A spotlight makes sense. Means like light is not always omnidirectional. Means for positional light, I would say many times spotlight. For directional light, there is no meaning of spotlight. No one can put a kind of a cone in front of sun. So directional light, there is no meaning of a spotlight. Though we can try getting that also, but it doesn't make any sense. But since it is an infinitesimal distance away from the position, so but for positional light, like we get a street light and those things. So for that, I think it's okay. But like a motorbike, the front light, so those are completely kind of. It is a cone light, so it is a spotlight. I mean, there is a cone that is fixed in front of a light, so that light will go in only one direction, or the light in other direction that doesn't belong to cone direction inside the cone, so that won't come. So spotlight that we'll see, then we'll see the attenuation, means positional light the way we saw. If I take away, if it is very near to the model, then lighting at every pixel in the model, it has the mercy of the shape of the model and position of the light. But if light comes away, then slowly it is converting into directional light, so it is getting full light. But that is not the case. The positional light, it gets attenuated. So either it can be quadratic attenuation, means 1 by d, 1 by kind of distance square, or linear 1 by d. So generally we go for linear attenuation. So spotlight, attenuation, and Phong model, per pixel lighting calculation. So that we will see. Okay, so we have finished everything except the spotlight. So that we will see. So spotlight is kind of light will be, one cone will be placed in front of the positional light, and it will kind of throw light as a, emit light as a spotlight. One spot, one beam of the light that will come. This is kind of, this beam is bigger, means angle is more, or light is far, light is near. And so this is the spotlight, and light decreases. So at the center of the spot, light is more and light decreases. Here, full cone, light is illuminated with the same intensity. So this is the spotlight. And attenuation, light can be attenuated if it is far. If it is near, then full brightness. If it is far, then it is attenuated, less light is coming. So these two things. So what we are talking is that we have already discussed. So this is a kind of a spotlight where we place one cone, and this is cutoff angle. So if cutoff angle is kind of theta, then 2 theta. If cutoff angle is 30, then 30 plus 30, 60 degree, it would kind of, it would illuminate. So if we see the net calculation of the light, so for each light source, first is attenuation. So this is constant attenuation, and this is linear, and this is quadratic. So we will not use quadratic. Quadratic means square times it will reduce the way if we proceed with the light. So it will become very dim. So only linear will use. So 1 by Kc will make 1. So or Kc will make 0. Then 1 by D. So this Kl also linear will make 1. So 1 by D. It will resolve to. Or we'll put Kc1, then 1 plus D. Okay, it is up to us how we want. And a spotlight effect. So spotlight effect is if light is falling outside this cone, then there is no light. And if it is falling inside the cone, okay, so probably we can edit this. Okay, so this is cutoff angle and this is spot direction. White line we are seeing, that is spot direction. So line, so it must fall outside. So if I save it, okay, so light must fall. So if light is in the spot direction, then if I place kind of there is something called spot exponent. So spot exponent means light, if it is falling in the direction of a spot direction, then it is the kind of maximum light. And if light is in the cone itself, light would vary. If it is going away from the spot direction, the cosine cos theta of the direction and spot direction. So if it is here at angle of 20, then this vector, okay, so this vector, whatever will from here, if we imagine a line and a spot direction, the dot means their dot product cos theta to the power spot exponent. Okay, so that is a kind of that becomes the spot factor. Okay, so if I draw a line this, so if I using the spot exponent, so if light is in this direction, okay, so I mean the vertex is in this direction, then it would expect a maximum. If vertex is in this direction, then nothing. If vertex is in this direction, okay, so at that time, so this direction will make as a since this is a spotlight, this is a kind of a positional light, so this would be L light vector and this would be spot direction. So if this is D and this is L, then L dot D to the power spot exponent is the kind of the variation. So if a spot exponent is 0, then if a spot exponent is 0, then there is no variation of light inside the cone. So inside the cone, it will be illuminated like this. Okay, if there is a variation, that the center, it will be bright, and as it goes out, it will be kind of fade, and anyway after cutoff there is nothing. So this is the calculation. Now we will go with the actual calculation, how it happens. Okay, so we'll bring it. Okay, so suppose our light is I won't say this as okay, so okay, so suppose the light is positioned here. Light is somewhere, it is positioned here. Okay, and I want to illuminate a point that is here. So the normal vector is this. So this is normal. If this is normal, if this is light, then this is light direction. Okay, so this is light norm. There is another thing that is called a spotlight. So light came here. Initially, probably light will be here only at the 000 or 00, some location 005, 003, so where we position. Since we did the transformation, so light came here. So the light spot direction, for time being, I consider the spot direction as this. Okay, light rotated, and this is the spot direction. What is the spot direction? This is the spot direction. So I call it a spot direction as D. If a spot direction is D and this being light direction, light vector, okay, and cutoff angle is some theta, that is this. This is cutoff angle around the spot direction. Okay, so this light, this point will not get illuminated because it is out of the cone. Okay, now think about if I want to illuminate a light that is inside the cone and it is here. Now the normal vector would be this. Okay, and line connecting the light position, and this is the light vector. So light vector and normal vector. If we do dot, then we come to line vector and normal vector. If I do dot, we come at the calculation of diffuse light. Okay, line vector and I coordinate, that we come in the calculation of a specular. Okay, but in the vertex. Okay, so probably I can save and okay. Okay, so we are talking about this. Now I want to illuminate a point that is inside the cone, and we draw a new yellow color normal and new light vector. Okay, so this color, so this is the new light vector. Now, whatever we do the dot, through that we decide for the diffuse factor. Okay, and if I do E dot n, okay, so this is n, this yellow line is n. So E dot n, E is this direction, I direction, where the I is. So if I do E dot n, then I get the plus L dot n, I get a specular component, diffuse component, a specular component. What about the spot factor? Okay, so since it is inside the cone, so that whatever comes as diffuse and a specular, so that's okay. This is what the spot factor is. But if I go for a spot exponent means the spotlight should decrease from the center inside the cone itself, it should decrease along the kind of boundary. So in that case, this is the spot direction. What we see here is kind of orange. Okay, so this is the spot direction. So spot direction and the light vector. If I do cos, if I do dot, whatever comes in, okay, so that, so here, so this is D and this is nu L. Okay, so this is nu L. It's a kind of reddish brown. So this is nu L. Okay, and this is orange color is D. So if I write like this, L dot D to the power spot exponent, how it would decrease, power spot exponent. Okay, that will be that much it would reduce. Okay, so L dot D, so D and L, if I do dot, then and then power exponent. So if I want to illuminate something at spotlight location only, so this is a spotlight location. Here, if I want to illuminate something at the spotlight location, okay, so if I want to illuminate something at a spotlight location, so at this case L dot D, okay, now L, the L would coincide the D. So L dot D is 1. So L dot D is 1. In that case, spot exponent, whatever it is 1. So it will get maximum illumination. So from the center of the cone, if I start going outward, the L dot D would decrease and so light would decrease. So that is signs of kind of spotlight. So what about if light position is here? Now I did a kind of transformation in the light rotation and light position is here. If light position is here, then the spot direction, whatever we are talking about, spot direction. So spot direction would also transform. Okay, so we can think at a spot direction now, something like this. Okay, or if we change the spot direction, then it is something like this. It is up to us what a spot direction we keep. If this is the spot direction, then it would illuminate only that comes inside the angle. Okay, and if I use the vertices here, that gets maximum illumination. If I use vertices that is at the corner, it gets less illumination inside the cone. Outside the cone, nothing. So this is spotlight. Okay, so we talked about the spotlight, and we'll add so whatever we are doing, we have been doing. So that is the vertex calculation. So this is what we have been doing. Now we will do kind of, so what is problem in the vertex calculation? So problem in the vertex, like whatever example we have pushed, that is kind of shaders calculation. So per vertex calculation is we get, so illumination happens only at vertices. So in the fragment shader, it interpolates as per the shading models. If it is a kind of smooth shading, so it thinks about coloring the rasterized pixels as per the vertices lighting. I mean, lighting anyway, it generates color only. So as per the vertices color. So at the vertices, if there is no illumination, there won't be any light. Okay. So to make it more perfect, we go for kind of doing the light calculation, doing the color calculation, doing the fragment calculation at each fragment, at each pixel, set of pixel. So that is kind of a Phong model. So we are doing right now per vertex model, that is kind of a Gorward model, and we will enter into Phong model. So Phong model would look like this. So if I do per vertex calculation, so if light color at the vertices are green, so full surface will be green. Even though we are kind of showing some kind of light at the center. Light at the vertices only matters, not at the, so if I have a big shape and less number of vertices are there and light is beam light, there is a high chance that light will fall in this region. If that is the case, then there is no illumination in per vertex calculation. Where in Phong model, we do the calculation per fragment, per pixel. So even though there are only 4 vertices, okay, still we get illumination on the surface. So each pixel gets illumination. So that is a kind of huge difference. So it makes sense in real life, but at the cost of too many calculations. Per vertex calculation is less. If there are kind of, like I have a cube, then there are, I believe, 8 vertices. But if I go for per pixel or per fragment calculation, it may go beyond 100 or 1000. So that is the difference. From 8 to 1000, so too many. So a machine has to be very strong and kind of highly powerful. So that is the idea. So we'll see that. So I'll delete this and we'll add. Okay, so we have added Gorward and Phong model. So that also we'll see. Okay, so we'll proceed now. So this is what code we had written till now. And now kind of we are happy that we'll proceed in the spotlight direction. So spotlight direction, as we discussed, so we'll introduce a spotlight direction called D. Okay, and D we will calculate like normalize. Okay, so transpose inverse model view light into whatever transpose. So we are making that D would also move if light position is moving. okay, dot x, y, z. That's it. So this is new d, and if this is the d, so we'll calculate the spot factor. Okay, so spot factor probably we can add here in float spot or its spot factor. I think it's not a good programming habit. So I can say spot factor. Float spot factor equal to 1.0. This is how we initialize. And now it's time to calculate the spot factor. So if light is other side anyway, we'll go with the ambience color otherwise. Okay. So otherwise we'll calculate. So if dot of L, dot of D and L, okay, is greater than cosine of the, okay, pi, I'll just calculating in hurry 3.14 into angle is 20 divided by, this is in radian, okay. So if this is the case, so we are inside the cone. If this is the, this should be equal, then we are inside the cone. If we are inside the cone, then we are happy to announce that the spot factor is modified power, okay, so max 0 and dot of D and L, and power by exponent factor. I'll make exponent factor 40. I think I can initialize with this with 0. So I don't need to put else. So it will be 0. If spot factor, if that is the case, then a spot factor is a nice one. Otherwise it is 0. Okay. Otherwise calculation is happening the way it is. And here I'll add a spot factor. Quite simple. Okay. So I introduce a normalized vector and a spot direction, that is transpose inverse model view light and into vec 4. So, and this is the initial direction, this is direction, okay, and then we did dot, and if it is inside the cone, then spot factor actually has some meaning, okay, otherwise it is 0. If it is 0, then there is no color. I think we are done, that's it. So I'll see what is option. So spare, so pretty well. Okay, semicolon I have to make. This is not a Python code. Okay, so pretty well. Okay, so finally we forgot the semicolon here. to the power 40. This is not correct. Max dot here. Okay, we'll try our luck again. Okay, so Mr. Transpose, so we have commented this as we did not needed this transpose and view light. Okay, so we will kind of add here model view light and transpose inverse model view light. So we'll get the uniform location of this one. So model view light, transpose inverse model view light. Now transpose inverse light. Okay, so I have to uncomment this, so they should go there. We'll try again. Oh, okay, so this is a sphere. Now this is light. Now I'll bring light near to the it became a spotlight. I believe it is quite clear. So it became a spotlight. Okay, so this is because of because of WYH. Okay, so this is how perspective projection is probably. Okay, so kind of spotlight is visible. Spotlight is moving along with okay, so I'll bring it again. There is no cost in bringing it again. So this is light and I am placing it near the spotlight is appearing. I mean, there is no harm in showing that. Okay, so I'll rotate it. Blue color is the ambience. So there is a difference. This is not ambience, what we see around the spotlight. That is black, there is no light at all. Okay. First idea is that I would show, so I can say that, okay, so whatever we are drawing, so we'll remember it. Okay, so this is what is with spotlight. And we'll disable the spotlight and we'll see what is the, so disabling is not very difficult. We'll just remove this spotlight. This is without a spotlight. This is with spotlight. At the beginning only there is a difference. Now this, if I place the light near the sphere, we can see ambience is kind of, it is appearing around it. Okay, and distance, how much it is? So if I print, it is minus 2.9, whereas here distance is nothing. Okay, now I'll take it to minus 2.9, so 2.3, 2.7, 2.9. So both are at same distance. So I'll remove the light, and here also I'll remove the light. Now see how much different it is. So the left side is without the kind of spotlight. Right side is spotlight. So spotlight and blue is the ambience, black is no light. So outside so if I bring it big, so outside, if the camera position is near, so if camera is near, light position is near, if light position is near, then since this is a kind of a positional light, so we see the ambience round. But here, in the spotlight, okay, we see black color. Means there is no light. Ambience is much kind of around. So this is spotlight. Now we don't want exponent, just a torch light. Okay, so I'm happy with this. And just a torch light. So I don't want exponent. Exponent is 0. It should be equal all around. I mean, this is better idea. Okay, so it should be equal all around. Okay, now it is equal all around. 2.9. Okay, so I don't know, sometimes it comes around. Okay, so it is equal all along and it is different than this. Both are different. Okay, so 20 degree is this much we are getting a smoother. Probably I can increase the angle, then it will be even smoother. So I'll make it kind of 30. Okay, it is like this. Okay, so this is what we are doing. Okay, I have generated this through fragment shader, so that's why it's smooth. So this much we get in vertices shader. Okay, so the per vertex calculation and per fragment calculation we are talking. So this much we get in the per vertex calculation. So this is a spotlight like a torch. No one stops us revolving it. It's like a torch. Okay, I can move up, move down, left, right. It's like a torch. This also I can rotate. Okay, move up, move down. So this is about spotlight that we have discussed. Okay. Now we will move to attenuation. So attenuation, light will decrease. So attenuation calculation is this. We have to place the attenuation like this. So we'll add. So probably we can kind of mute this. Okay, so what is Mr. Attenuation is? So we'll introduce attenuation. Attenuation. And now I will calculate the attenuation, whatever the attenuation. Okay, so attenuation matters between distances. What is the distance? Okay, so distance is light position. What is the distance? So distance is light position and vertices. If this yellow color is the vertex and this is light position, then this is the distance. This much is the distance. If distance increases, light should decrease. Okay, that is attenuation. So what formula we will, so first we have to calculate the distance. So I would say, okay, so attenuation instead of, so we'll calculate the distance. So I'll say, I believe a distance we can just add it here. So I can say float distance between light and vertex equal to 0.0. We'll calculate the distance. Distance light and normal, light and vertex equal to distance model view. Okay. Now both we are transforming. So model view light into vec. So this is the we are not using too many variables here and there and storing. We are using right now, this is for demonstration purpose, x, y, z and distance between and model view sphere into 4 and then whatever the coordinate is, sometime it is called I coordinate dot x, y, z. Okay, so this is distance and this is model. So we calculated the distance. Now it is nice idea to calculate the attenuation. So attenuation equal to, so we'll clamp between 0 and 1 and I'll say 10. I'm using 10 so that there should be some light, means it should not go too low, and we'll clamp between 1.0. Okay, so this is attenuation. So finally we calculated the attenuation. And since we are doing all the, it's not very wise anyway. I mean, this is not a kind of a very optimized code. Optimization we can do. So this is for demonstration, and here I'll add multiply by attenuation. I mean, this is what it is. Attenuation, spotlight effect multiplied by ambience multiplied by diffuse multiplied by specular. Okay, this is what exactly we are doing. Attenuation multiplied by spot factor multiplied by color, that is specular into diffuse. Ambience we are calculating other way. Okay, we can add ambience in this multiplication also. There is no harm in that. Okay, now it is done. As per the discussion, we can add in the attenuation here also. We talked about distance, so kind of 1 plus, this is the formula, 1 by Kc plus Kd, polynomial, quadratic we are not using. So, okay, 10 by 1 plus distance Lv. Okay, so we are done. Probably it should compile and we should get some output. Okay, so we'll make it 40. Python. Okay. Now, if I take the light position kind of far, then okay, I can try other thing. So we'll use a sharp image. So here I will use whale shark.org. Okay. So this much light it is receiving. So if I bring the light away, it is increasing. After that, light is decreasing. Means this is the light position. Okay. So this is the light. If it is near, I believe it is too low. And if I bring it, so this much we don't like this because we are using our great spotlight. So that's why it is showing, we are not able to see attenuation nicely. What I can do, and I can kind of mute this spotlight effect right now so that we can see the attenuation a little better. Okay, it is far better. And so I can bring away. So it went really away, but we are seeing the attenuation. So okay, so it is becoming dim, and so if I bring near, it is glowing. Okay, now since it is positional light, so if it goes inside it, then again it will be nothing. So only ambience we can. This is ambience. Okay, but if I bring it light position away, then it will become dim. Okay. Now I am bringing light position near to the model, so it is becoming bright. This is ambience. Okay, I can rotate the model also. Okay, so this is attenuation. Okay, so we'll move to So we'll move to much awaited kind of fragment shader. So fragment shader where we do the all calculation through a fragment shader, not in the vertex shader. So that is the Phong model. So Phong model we'll see. Okay, so this is Phong model. So this is whatever we are doing, that is per vertex calculation. Now we'll do per fragment calculation. So that is the idea. Okay. So we would comment this. It's in Python, it's like the way we wish we do. It is that simple. Okay, so 71 and 14. Okay, so 14 to 71. Okay, so this is our new vertex code too. And this is okay, sorry. So copy paste happened. Okay, so this is vertex word code, whatever is the original we have written, and this is what we'll modify. Now things would move in the kind of a fragment shader. So probably okay, so how I can copy their things, because it is exactly same. So probably I can type it here only. So I would say we need a projection, and we need model view sphere, and then we need these two attributes. So this would go here, and I would say void main like this. So we ended this code, and here inside now we will have varying. So there are two varyings. So varying one is vertex coordinate, and another varying is normal. And here a GL position, this code we will just bring it here. Okay. What is these two varyings? That we'll put it here. Okay, so vertex coordinate is nothing but coordinate, and normal is nothing but normal. So we are passing the coordinate and normal to the fragment shader. We are doing nothing else. So projection and model view sphere, what we are receiving, through that we are doing the transformation in the vertex. This is what is expected from the vertex shader, and then we are moving the vertex coordinate and vertex normal to the fragment shader. Okay, so we are done. Now we will stick the kind of label here of the fragment shader. So you are Mr. Fragment Shader. So this is fragment. Okay, so version is not, I think it supports 330 also. So and we are using pip3 through a Python installer. So we are using sudo pip3 list and grep -i Python OpenGL. It should come quickly. Okay, so there is nothing like that. I would say OpenGL. Okay, so py OpenGL is what we are using. 3.1.7. Is there anything like show? Okay, so author is Mr. Mike, and I tried to see, so show when it was released. I believe it is released recently because, okay, it is based on Python 3.7. Okay, anyway, so we can continue with our business. Okay, so vertex code shader we have finalized, and in fragment shader we have projection and then all the thing, and then lit also still we have. Okay, so two wirings are here, so these two wirings will come here also. So where it vertex color is no more a wiring. Okay, and now we have diffuse color, specular, component, spot factor, distance, attenuation. If it is lit, then that's it. Nothing more. Okay, now wherever we have coordinate, wherever I'll replace with a varying vertex coordinate. Okay, that's it. And wherever we have normal, we replace with vertex normal. Okay, so only one place. Normal. Okay, vertex coder. Normal. Okay, so I think we have changed. Okay, so a vertex normal we have used only in calculating the, while calculating the normal. Okay, so when we kind of transform the normal from a vertices, then we use n. L is light and distance, attenuation d. Okay, and so what we are doing here means why it is different when code is same. We are using, it is called interpolated normal. Okay, so what happens behind the scene? Anyway, first we'll see the output, then we'll calculate it. So this is, now we'll go down. Okay, so probably we just remove this. This is the main, and now wherever we are calculating the vertex color, so it is now GL frac color. Okay. That's it. We're completely done. Oh, vertex. Okay, so what we are doing, so let's see. So we are using a spot factor as 40, very well. Attenuation, we can just silent it for timing now. And attenuation will remove. So only spot factor will focus. And that's it. So we'll try if it really compiles. First of all, we are seeing issues in compilation. Okay, so GL frac color is undeclared. Not bad. Okay, so we can see the spotlight and how it will be different. So better we'll use cone, because now I have a cone that has 4 vertices at the front and 4 vertices behind the scene. Okay, so that we'll use. So we'll use cube which has 8 vertices. So I'll edit it and we'll use, instead of it, we'll use cube. I'll copy cube, image globe, okay, and then we'll try. Okay, so now we can see that even though illumination is inside the cube, still illumination is there. Okay, this is what it is. Okay, we can see the shining at the center. I can increase shining. So now we'll run both. It's not that we are showing in one corner. So we are using a spotlight. Okay, so time being will kind of a spotlight will remove the exponent part, and here we'll use a specular component bigger so that it would be visible. Okay, so this is what I want. Now we can see okay, so we can see the shining at the center. Now if I move the light near to it, it will become a spotlight. Spotlight is inside the cube, but it is still showing. We can see the blue, that is the ambience, still showing. Okay, this is per vertex calculation. Oh. Okay, so this is per vertex calculation. Okay. Now we'll use a per vertices calculation. We'll retain the code. So this is the code for per vertices calculation. And so I'll remove this, I'll place it here. And we'll use all the factors what we have used same. So I'll use here color of shining as 8. And we'll use no spot exponent, that's it. And then we'll draw it. This is per vertex calculation. Now I'll show the kind of spotlight. There is no light, only ambience. I think ambience is visible, that is blue in color. There is no light. Spotlight is falling on the surface. That is not, so vertex is not included. If vertex is not included, there is no light. So I'll bring the light. Okay, so this big is light. Okay, I'll bring the light near. So now vertices are being illuminated. I have to use bigger projection matrix. Okay. There is a specular shining if you see. If light is falling on the vertices, see? See? It is pretty clear. If light is falling on the vertices, then there is a lighting at the corner, and that is what it is kind of interpolated around on the surface. But here, doesn't matter, means I'll bring the light near. Doesn't matter. Okay, light is falling at the vertices, it's luck. Otherwise, it is also okay. Okay, whereas per vertices, lighting is falling is at a vertex, then it is very fine. Otherwise, there is nothing. Okay, only vertices, near the vertices it is shining. Otherwise, there is absolutely nothing. Okay, so a difference is kind of, it is visible. So left is per vertex calculation, right is per fragment calculation. Okay, so how it happens? When it does the computation, okay, so right now, if it does the computation, so in this fashion, so this is our cube. If this is the cube, and we have normals only at the vertices. This is normal, this is normal, this is normal, this is normal, and this is normal. Okay, so if it is doing per vertex calculation, then it is estimating the normal as these locations. This is called interpolation. If I am using a smooth model, then whatever the vertex, what is the normal near the vertex, that it is taking. And per pixel, it is estimating the normal. Okay, nice would be if we do the calculation per pixel the normal, not we let the kind of OpenGL do, because OpenGL will do kind of universal calculation, may not be fit in our calculation, but it's okay. Means for timing it's okay. Okay, so that is the scenario. Okay, so I believe it is really nice. Okay, so we have finished lighting fundamentals. We saw Gorward and Phong model, and spotlight attenuation, and ambience diffuse specular, and positional light and perspective projection and directional light. Okay, and then all the topics. So for the spotlight, if I see the calculation, for the spotlight, D equal to, we are using directional. Okay, we are not using positional, it is fixed. We are not transforming the spotlight with the model view light. If you see the normal, we are transforming it with model view light, whereas we are transforming it with transpose inverse model. We are considering this as a normal, as a normal surface. Okay, so that is the calculation. Okay, otherwise code is same. Okay, here nothing. Whatever, only vertices are shining.